So hi, today I think that's the second of our ROMER talks, and we have Utku Çulha today with us. And firstly, thank you for joining us today. And actually, Utku Çulha has received his BSc and MSc from the Bilkent University. Then he completed his PhD in ETH Zurich, and I think after that he worked in many reputable institutes, including University of Cambridge. I see Stuttgart Intelligence Systems in Max Planck Institute, and now he's in the Technical University of Munich, and he's working on the Robotics and Machine Intelligence Institute there. And he's mainly working on the, I think he will mention anyways, but bio-inspired robotics and soft robotics. So Utku, stage is yours, so please proceed.
Well, thank you very much. First of all, thanks very much for your kind invitation. I have been around a little bit, but half of my life and my heart is still at Ankara, Bilkent and ODTÜ, so I always feel at home when I make connections with my friends, my fellows, my PIs in Turkey. So I feel home. Thanks very much for inviting me home again. Today, I tried to bring together some of the stuff I've been working on, and over the years, like Ozan has briefly described, and I would like to talk about these, and maybe we go into a little bit of detail why I'm doing this as well. So maybe I'll just, I think this is already, Ozan already talked about this, but
yeah, don't worry, you can go on.
Yeah, so again, my home is Ankara, so I left in 2012, and since then I've been wandering around like a true Turkish nomad here and there. And for the last 5 years, I'm in Germany, and after visiting these places in Europe, Central Europe, Northern Europe, I've been working as a chief of science for the last year at the Technical University of Munich. I'm the scientific manager of the Munich Institute of Robotics and Machine Intelligence. I believe it has a lot of fundamental connections with ROMER. And that's why maybe if you like, we can also discuss in detail what could be the synergies, what could be the things that we could do together, which I would be very interested, to be honest. So that's why I feel more connected to the ROMER's vision and ideas, and I can totally see the hurdles, and I can totally see the vision there as well. So maybe I'll start with the institute that I'm scientifically leading at the moment, and then after this brief introduction, I'll get back to what I have been doing for the last 10 years, maybe more than 10 years on robotics. So our institute is quite the latest push from Technical University in terms of trying to be a little bit more international. TUM, which you would be surprised, is quite a conservative university. It's quite a conservative German university, and they have their old German system about becoming a professor, all the rules and bureaucracy and everything. But interestingly, it's one of the top schools at mainland Europe in terms of especially with engineering. And with the latest push from the president, they wanted to turn the departments into institutes so that it's more multidisciplinary, more interdisciplinary. So we are one of the institute that is basically the amalgamation of several chairs. So Robotics and Machine Intelligence, our integrated research center, is one of the ones that has been established first. And we are basically the flagship of all the integrated research institutes. Sometimes it's a good thing because we've been publicized a lot, and we're getting a lot of help and funding. But on the other hand, as we are doing the things for the first time, we're facing a lot of resistance from the system, from the old type of university management. So it's an interesting challenge. What we do, as the name suggests, is a combination of what's happening here? I hope I didn't crash anything. So it's a combination of basically four areas of the robotics and machine intelligence. We are doing research on robotics, perception, AI, and machine intelligence. It's quite important that we are just saying it multiple times. We are not really doing data science. We are doing all types of machine learning applied on physical systems. So we have another completely different institute that does data science, all types of learning using deep learning, neural network, all things like this. We are all interested in things that are applicable on hardware, robotic hardware, not computational hardware. So we have something around 62 professors, each have their own chairs, and they bring together their expertise and vision, and we apply these vision into 4 main categories. These are our innovation sectors. We have 4 of them. One of them is environment, the other one is health, one of them is work, and the last one is mobility. And those are the basically innovation sectors that we put together all of our expertise and make connections with the society and the industry. We have our board of directors, and we also have a scientific advisory board. We also have the industrial advisory board, which is quite a unique opportunity because we are able to sit together with C-level people of some of the top industries in Germany and in the world. So maybe I'll just go here. What happens? Sorry. Okay, so one of the things that we do here that is quite the driving mechanism behind all of the research is the Lighthouse Initiative research stories, research projects. So these are the ones that actually bring together multiple PIs from different departments. And those are the ones that we get a lot of funding from the ministries. We get funding from the German research foundations and the industrial partners. And those are the ones that have really big visions. Some of them you see on the screen now. We're having collaborations with different universities and different industrial partners in different parts of the innovation sectors, from communication, health, work, and mobility. So these are the ones that really make our institute a little bit more on the edge, because we are doing real world applications with real world science. So there's actually little space for futuristic, maybe, exciting stuff that on the paper, but not really applicable in the real world. We are trying to really minimize that type of research in our institute. I am, as a part of the senior management here, as I'm leading all the research activities, meaning on paper, I am doing all the research coordination between these 60 professors, but thankfully they're not all of them active. So it's actually a good thing at the moment they're not all active, but I am working with all of the professors. I'm responsible for writing big proposals. I'm also a PI. I have my own research team. I work closely with the students and postdocs. For the moment, I'm also leading a team of approximately 80 people. Some of them are, I think 50 of them are PhD students, 12 of them are postdocs, and there's also an engineering team. And the people you see here are also the ones that are managing the whole institute. So we have people, board of directors, those are the PIs coming from different chairs, and we have officers and assistants. So I believe that's also quite a synergistic connection with ROMER as well. So as I said, we have connections with the industry. Those are the C-level, basically CEO or CTO level people from the well-known industries. I find it to be quite unique and actually advanced that we get to sit together in the same room with these guys. They're really sparing their time for us, and they can really tell us what's missing in the industry. They really drive us, and they really drive the research accordingly, so that we know what is basically needed in the industry, so we can come together, sit together, and drive research and industrial projects together. Just like the industrial advisory board, we have a scientific advisory board. Those are also well-known names from robotics and artificial intelligence all around the world. They're helping us in terms of our internal funding schemes. They're helping us by reviewing the process of our project proposals. And in the future, we also have plans to get them involved in other projects as well. So that's basically the institute. If you like, we could get back to it at the end of the presentation, because I'm going to talk about what I do research-wise in the institute as well. So I would like to maybe start discussing what I have been doing in terms of robotics for the last more than 10 years. And the way I describe is the bottom-up design and control methods for adaptive robotic systems. What I have eventually carved out of all the research that I've been doing was bringing these two design methods together. At one hand, we have the typical top-down method that we have been applying as humankind for hundreds of thousands of years. Basically, we start with an idea of a final image of what we would like to build. It could be a robot, it could be a cake, it could be a space station. But we always start with that big idea, and then we build things together with that top-down design. And of course, it has given us all degrees of freedom in terms of autonomy, programmability, and optimization. But the more I started working with soft elements and small-scale systems, I realized that the way things are built in nature really follows a different agenda. The things actually come from the bottom up. They're little things, they're really dumb and passive. They don't have any idea about the world or have any idea about anything, basically. But through local interactions, through some external stimuli, maybe, and with given millions of years of freedom, they come together in meaningful and maybe just basically operational systems. And as compared to the other top-down methods, we see that things that are built by bottom-up methods, they have quite a high adaptivity capacity, they have degrees of freedom, they have modularity, and more and more we see actually, and we see these methods applied in robotics as well. For example, Professor Shine is one of the pioneers in swarm systems. I'm pretty sure that he has been applying these methods in control and planning and the flock management of the swarm systems. But more and more with the smaller scale systems being introduced in robotics with functional materials, we see that they are also being applied in soft robotics. And this is the connection to what I have been doing for the last 7 years. So my goal is to really find a middle ground in between and hopefully get a happy marriage between these two systems. So I am coming from a robotics background, and I am still having some type of OCD about introducing some type of a control and planning into these naturally chaotic systems that are being built on the bottom up. So this is my main motivation. I'm trying to get the systems that we know in the conventional robotic systems and try to apply them to the bottom up systems in self-assembling and soft robotic world. Actually, I have chosen the human hand as a perfect manifestation of all the research topics that I have been working on. One of them is the hybrid systems that combine soft and rigid elements together. The other one is the self-assembling bottom-up systems that are being built by using small systems. They come together, they're modular, and they bring together something more than the combination of the systems. And the last one is basically lifelong or machine learning that will tell us what has been missing in the whole function and morphology and the control, basically investigating the things that are not obviously clear or apparent at the beginning, but then help us to explore what's behind what we see in the robotic systems. So one of my research focus is the hybrid robotics. I call them hybrid because of the combination of soft and rigid materials together. And I have been working on the design and modeling and fabrication and control of these robots that are made of these soft and hard systems together. And these are basically the pillars of the robotic systems. You have the design, you have the materials, then the prototyping methods, you have the modeling controls, and eventually I managed to bring all of them together into adaptive manipulators. That's basically the story of where it starts, from the design to prototyping to modeling control and eventually building adaptive manipulators. One of the earliest things that I have done while I was doing my PhD was to investigate how we can really understand soft materials, how we can model them and benefit from this modeling and control perspective so that we can maybe explore an interesting adaptive sanction mechanism. What you see on the left is a very primitive sensor system. It's a robotic arm, very simple robotic arm, as you can see. But what we have is attached to the end effector is a hot glue extractor. Basically, it's the ones that you use to glue things together. And it's basically a 3D printer, but 3D prints a hot glue. So we have basically modeled the adhesive and extruding properties of this hot glue, and then we turn that into a very primitive sensing system such that the robot, for example, I'll stop it here on the video, prints this stick, a long stick. We know the modeling of the stick, we know the bending models and everything, and then the robot basically prints that, attaches it onto itself by the adhesion properties, and then goes ahead and then explores some objects in the environment. Very primitive. And through the modeling of the bending beam, we know exactly how much force would be necessary to bend this specific beam. And through that, the robot has an idea about how soft or how rigid the system is, the object is. With using exactly the same system, exactly the same material, but just changing the morphology, we are able to now sense temperature. But please keep this in mind, it's a very primitive sensing technology, such that this piece, this volume that we print, we know the weight of it, and we know exactly how much heat needs to be transferred such that when it touches a hot object through the heat transfer, we know the adhesive properties, we know at certain temperature, this is going to melt down and drop. So in a way, it's a very simple binary sensing system. It's like, it's hotter than this temperature or colder than this temperature. In a sense, that was one of the earliest methods of exploring adaptive systems. Again, by introducing the control and methods of modeling and simulation to a continuum world of soft material in terms of extrusion and adhesion. This was the second thing that I have done, basically following the same idea. But here we are now talking about something a little bit more advanced in terms of sensing capabilities. This was the time when I was in ETH. We worked together at the materials department called EMPA. They're basically amazing institute. They invent tons of different materials, but sometimes they don't know what to do with them. So this was a perfect collaboration. They had this material called the conductive thermoplastic elastomer. It's again a thermoplastic extruding system, and this time you have conductive carbon filler in it. And the way you put together, it's basically you generate a homogeneous material, and then interestingly, when you put this in a voltage divider circuit, it behaves as a resistive sensor. So nice thing is, with respect to the ratio of materials and the way you build it, it had linear response to strain. So we were able to generate resistivity versus strain matrix figure, as you can see here. At a certain level, you can get linear response to the strain. So what you do here, you basically generate a voltage divider circuit, as I say. You put this material on top of your soft elements, and then you can see, as in the video, you can generate a strain response from the system. And then the way I worked on this was basically modeling the deformation of the system. It was on the surface. From the surface, we were extracting the strain information and just basically connecting the dots in these, old puzzle magazines. You were able to generate a custom morphology that is unique to detect the certain strain information that exists on the surface of the soft material. And with this, we were using this to define our custom morphology. Because this was a linear combination of certain strain regions, we were able to optimize the signal to noise ratio, and then we were able to get unique information. So excuse me about the hand gesture here. I didn't know. We were trying to show the letters of our institute, ETH. This is the American hand signal, hand language. So what you're seeing here on the on my glove, that's me. You can see that on the middle finger, you see these two sensors. Those black things are the sensors. And from two different joints, we were able to get unique information. And with these two information, we were able to basically understand the type of deformation and then convert that into a sign language. Quite primitive, but still the idea behind this one is applying methods of modeling and control so that we were able to generate sensing for soft robotics. That's the main idea. And we went on and we applied this to very common deformation types in the soft robotics world, which is basically bending and twisting. And we were able to generate information, sensing information for soft robots. So this was sensing. That was one part of what I have done. And this was basically, what do you call this, like a side project. We wanted to see if we could really make use of the same model that we have developed for the extrusion of that hot glue material. By the way, it's just the Patex hot glue. You can just buy it from every convenience store. This was basically my first half of my PhD. I burned myself quite a lot, but I learned a lot about this glue. It's quite an interesting and educational tool, by the way. It really allows students to build fast prototypes very quickly so that they can really build things with their hand and see how they move. And then we really made use of that in the education part as well. We made a lot of workshops. We gave this to students, and then they built these robots. We gave them actuators, self-propelled systems, and then we asked them to put these together so that they build crawling robots. And that was actually quite interesting. So what you see here, I think I already teased it a bit, is the same extruding mechanism applied on a small mobile robot. We called it Spider. I don't think it's very obvious that it's a spider, but the idea is that this extrusion mechanism is coupled with the actuation mechanism, which is basically two wheels pulling the extruded drag line from the extruder. And this is a spider because it's generating a drag line as if a spider is descending from the ceiling. So the whole system is coupled, meaning that the extrusion and the actuation mechanism, they're all together. And then we have a full model of both the extrusion and the actuation, such that we were able to generate this drag line while the robot is still descending from the ceiling. So once it starts from the ceiling, so you have to attach it, obviously. What you don't see on the top is it's actually attached. So on the top here, it's attached to the ceiling, but it generates this drag line while it's being pulled down by gravity. So we could model all the extrusion parameters so that we can change the diameter of the drag line, we can change the speed of the robot. And the idea is that we were able to basically show that once we applied this modeling and control, you were able to generate a different type of locomotion in free space. So this was basically the first half of my PhD, where I worked a lot with the soft material, the hot glue. And then I went more towards the field of combining these systems together. This is how I am coming to the human hand as the perfect manifestation. So one idea we had was to introduce softness into robotic manipulators, such that we introduce adaptivity, but at the same time, we still wanted to remain in the robotics world. So we didn't want to go full soft, that we don't have any idea about what's happening. So this was our initial attempt of building an anthropomorphic robotic finger, such that we have rigid elements like the human bones, but unlike the typical the hinge joints that the robots have, we have these soft joints. Basically, it's like wrapped around by tendon-like systems. We have shells that are basically covering the joints. So with the joint geometry, which guides the motion, and with the shell that is covering the whole joint, we're able to generate a freedom space that is beyond the joint motion. So that, like what you're seeing here in the bottom video, for example, when you crack your fingers, the joints are able to move beyond their original axis of motion. So this gives the hands a little bit of adaptivity, physical adaptivity, such that you really don't have to model everything 100%. What you don't see here actually is below, maybe you can see it here, there are 14 different tendon systems that are pulling all of these joints. And this was a crazy redundancy. Actually, it's not a redundancy, I'm sorry, that's a mistake, it's under-actuated system. Even with these 14 tendons to 2 fingers, we had very little idea about forward kinematics. So we couldn't really implement just a forward kinematic approach such that you move the fingers into a certain position. What we did instead was to apply machine learning. I got inside this motion capturing systems. I was, using my fingers, and there were a lot of cameras with point markers. And then we were trying to use neural network systems to map those finger motions to basically the tendon actuation. We were trying to generate a Jacobian with the machine learning here. So that was the missing point between the soft systems and robotic control. One interesting thing was, I think there's still the potential here, and I'm very much still interested in applying these things. This is one of the projects that I'm doing here as well. So these hands are quite interesting in terms of their physical properties. You're able to load potential energy on the joints because there's flexibility on the joints. You can basically flip a coin, just like you see on the left side. So that's quite a hard thing to do with typical robotic fingers because you really can't, unless you have a stiffness, a variable stiffness actuator or joint, you're not really able to store this energy. The way it acts as a physical dampening system, the way that it has this adaptivity such that you hit and it doesn't break so easily. On the other way around, you can really store energy on this, and then you can do dynamic motions like this. And at that time, this was in Cambridge. Sainsbury, that's basically the equivalent of Migros in Turkey, but they produce their own produce. They were interested in applying this fingers, robotic hands, in collecting lettuce, which is quite a tough robotic challenge because the lettuce is quite soft and you want to pick it up without exploding it. So it was a good application field that shows how we can use soft and rigid systems together. And eventually it turned into a startup company. I guess they're now applying that onto the fields. So that was basically my PhD. Then I started working on self-assembly processes because I wanted to take this research towards self-healing or self-adapting systems that are more like cellular systems. And that is why I moved to Max Planck Institute to work a little bit more on the self-assembling systems, because they were experts in small scale soft robots, small scale magnetic systems. And my idea there was to investigate this dynamic world of self-assembling, self-organizing systems, which is beyond my capacity. I can easily acknowledge that this is too much to handle, all these Brownians and all these dynamic systems. But I still managed to scratch the surface a little bit so that I understood a little bit of this self-assembling, self-organizing systems. That what's the balance of how much you can introduce control and how much you can introduce modeling to a basically naturally chaotic system, such that it still explores a lot beyond the human control, beyond the human foresight, but still you're able to operate these systems and they do the things that you want them to do in human lifetime. So my idea was to basically look at reprogrammability, guided self-assembly, and then taking these things into functional robotic assemblies. I had the chance of getting a Humboldt scholarship there, which gave me the freedom to not worry about publications for 2 years. So I was able to really go into understanding the self-assembly world. And what I wanted to do there was really, again, scratch the surface a little bit so that if we could really use macroscopic systems and really apply self-assembly, self-organization plus control, so that I wanted to investigate how these robots can come together. I'm pretty sure this resonates a lot with Professor Shine's great work in terms of swarm systems. But I try to do these things with much, much simpler and much dumber particles. What you see here is basically 3D printed particles. These are, I think they were like 3 millimeter in diameter, 5 millimeter in diameter, I'm sorry. And you had a magnet inside them. All of them had a permanent magnet. What I did was I placed all of these things on a system like this. What you see here is an explosive view of the system. It's an external control method that basically changes the free space of these particles. And each of these particles, as I said, they have a permanent magnet and they're all in the same orientation. So if you squeeze them in a 2D world, they're repelling, right? And once you squeeze them all together, they're going to repel one another. And then in order to apply the same type of Brownian systems, I needed some sort of a self-propelling mechanism for these particles. What we did was to put all of this system on an orbital shaker that generates the kinetic energy to these particles. So you can imagine that these particles, with the given space, they all move around, they shake. And then what we wanted to do was to see if this control method, which is basically squeezing them, it has a lot of connections to material science, by the way. But we were extremely careful in not making one-to-one analogies because we got rejected multiple times. So that's the curse of working in multidisciplinary world. You have to be really respectful and careful in what you're basically saying. you have to say this is a Brownian-like motion. This is like an annealing-like work, because what you're doing is trying to do the same things in the macroscopic world, which doesn't apply. But you got the idea. I hope that we wanted to find the interplay between this free motion and then the external control, such that the question was if we can really change the speed of the annealing, the speed of the compression, to see if these particles will end up the formations that we want. Because what you're seeing here is just one example. The more you squeeze, because the particles are repulsive, they all try to repel each other, even though the whole system is shaking like crazy, you are basically trapping them in a magnetic potential lock, because they can't move anywhere. There's this balance between the magnetic force and then the mechanical force, so they can't move. And they basically freeze in time and space in different configurations like this. And we wanted to investigate what's the connection between that control method, which is basically the speed of compression, to the final patterns that we get. And what we are defining as pattern here is very simple. We had these 25 particles here, and eventually they all freeze up in these different circular formations. And we wanted to see if there's a statistical connection between that and to our control method. I hope that you see that this is really trying to introduce some sort of a control method to a very statistical system. And we managed to extract some statistical information out of it. I'm going to give one example. I think that's the simplest or the easiest one to understand. And it has a lot of connections with the material science as well. The slowest compression speed, the slowest annealing, basically, or the more time you give for these particles to find their best location, we ended up with a pattern that has the lowest magnetic energy. And the way we describe magnetic energy is basically the potential that is calculated in between each of these particles. That makes sense because all the particles are really trying to explore the whole space to find the best position that is almost symmetrical. So that was, for example, what you see here on this graph. The slowest compression method gave us, I think it was 96% of the time, the lowest magnetic potential pattern. And I have to tell here, I have done thousands of physical experiments to really talk about such statistical significance. And this was an interesting project that I managed to apply robotics and automation, because the whole system was automated, everything. The whole capturing and the whole restarting of the experiments, restarting of the systems, and everything was basically automated. But I think maybe this is an interesting take-home message. I have spent maybe months on making the system reliable and repeatable, which I will talk about later, so that I could take a coffee break while the whole experiment is running in 1 hour. So that's an interesting trade-off. And there was a slightly, maybe a little bit too much forcing here, but there was some sort of application that we thought of, because these are magnetic systems. You can imagine that that's a variable stiffness mechanism. So there's a torsional spring, because depending on where the particles end up, they generate a force on the leaves here. And so you can imagine that could be a continuous variable stiffness mechanism. Also, you can imagine that because there's also a magnetic field on top of the system, you can imagine that there's a magnetic gear that you can change the property by changing this method. So that work actually took two years to really go into detail, and then I explain what's the control method, what's the model, how you can explain these things. And then after 2 years, we were able to provide the same approach to a little bit more fun, more robotic application. Here, what you see is a family tree. It's basically a connected graph. What you're seeing here are 4 different pieces. The rectangular, the cheese-looking thing in the middle, not rectangular, sorry, triangular, is the hub. It has magnets on it. And all these little 2 dot arms, they're basically magnetic arms. They are connected to one another with a soft system, and they also have magnets in it. But unlike the previous one, we have an attractive interaction between these arms and the hub. So arms repel each other, but arms attract arms attached to the hub. So the idea is, given these 4 particles, how can we introduce some sort of a control, external control method, while these are freely rotating around? How can we introduce this external control method such that all of these particles end up the way we want them? And if you force enough, you can imagine that each of these structures, let's say, can represent some sort of a robotic system. For example, if you have all three arms attached to the central, we call that a mother bird. So like all arms are connected. And we wanted to see if we can get from completely disassembled system, and then we introduce the control, and if we can really use the graph theory here to guide the whole assembly towards the target assembly. And in this case, the mother bird that we want to do. So compared to the previous one was kind of an open loop system. We just wanted to apply the same external control method, which was the speed of the compression, and finally take the final image. So that was, in a sense, a much looser feedback system. And this one is a real-time one, which means while the systems is working, we are constantly monitoring the system. We take snapshots of the system, of the dynamic system, and then by using this graph, we are associating the current state to where we are in the whole state family to see where we are in the whole guided process. So starting from the completely disassembled system, which is basically the top, you have the hub, you have the central body, and then you have three arms all separated. And we take snapshots to see what we are doing, if what we are doing is really going what we want. In the previous one, the control input was comprehension speed. And in this one, it's the rotational orbital shaking frequency. Basically, we can slow it down, we can speed it up. And we worked a lot in terms of introducing how much that corresponds to the forces that are being applied to the systems. We have magnetic attraction, we have magnetic repulsion, we have the impact forces, we have the centrifugal forces, for example. Each of these we were able to relate to the orbital shaking frequency, so that when we take a snapshot, for example, this one you see here, we can see that this is a point where we can't really track and come to the final target. And this means, for example, the two arms are attached too close to one another. It means we can't really go ahead by applying the same approach. This means we have to change the frequency so that the system is disassembled and then they can be assembled again. But for example, for a different snapshot, let's say have a look at this one. So the arms are actually attached like this. So we can apply a certain frequency of orbital shaking so that it follows this graph here and eventually it reaches the target assembly. So what we can do when they're all assembled, based on how they assemble, as I said, you can attach some sort of robotic function to each of these. So the top one, because these are also magnetic, you can also apply a magnetic actuation to move them around. You can just generate this propeller motion and so on and so forth. So that was the self-assembling world. As I said, that was quite a big quest in terms of scratching the surface and understanding the self-organization and applying some sort of control methods to see if we can really guide these systems into what we want. What we have done later on was to apply machine learning methods into soft systems and self-assembling systems, which are basically lacking the connection between the input and output functions. So in general, you can say that they are lacking the Jacobian a lot because of the way they're built, because of either they're very statistical. And this is the point where we started applying machine learning on these methods. And this was my last years in Max Planck Institute in Germany. And here we started to implement if machine learning could extract the controller parameters for soft scale robotic systems. And the idea was to have these soft continuum and external actuated magnetic robots, which had really not so clear control parameters. And we wanted to really go into the detail of finding the optimized control parameters for these systems. And the next steps would have been extracting the dynamics and kinematics of the systems, and then basically lay out the unknowns of the soft robotic world in the small scale. This was a work that I had the chance, I think I have seen his name. He was in one of the audience, Sinan Özgün Demir. I had the chance to work with him in Max Planck Institute. He was the one who really took the whole system from the bottom and then really brought it into a very adaptive and trustable system. So what we did was we took one of the flagships of our institute, which in terms of publication, we took a system like this. What you're seeing here is I'll stop the video here. If I'm not wrong, this was a 3 millimeter length, 3 millimeter long cast robot, which had magnetic particles in it. The way you do is you basically mix these particles together in an elastomer compound. And then once you apply a very strong magnetic field, while the robot is basically in a certain position, the magnetic orientation of the particles are basically fixed. And once you reapply a magnetic field that is actually weaker than the original one, you can generate a magnetic torque around it. So the particles basically try to align themselves with that magnetic field, and then they generate this torque on the robot. And that's basically the premise of the whole magnetic actuation in magnetoelastomers. So the idea, this was one of the flagships again of the institute. They have generated this crazy little robot by applying different magnetic directions and frequencies. You can make it walk, you can make it jump, you can do a lot of things. But we got a bit OCD about this as roboticists. We said we wanted to really understand if you can fully control the system, if you can really make it repeatable, trustable, because the whole intention of using these systems was to put them inside a human body in medical applications. And without full control, we were not very comfortable. So what we did with Sinan, we looked into the control parameters of this, and we realized that it was not really repeatable. So Sinan built this magnetic coil system with the camera all around, so you could apply a three-dimensional magnetic field, and you can change the frequency of it, you could change the orientation of it. This is, even though that's a very small system and the control parameters are quite actually limited, if you wanted to apply a typical explorative sort of approach in terms of looking at all the parameters, you would have to do hundreds of thousands of experiments. But we didn't have the time or patience or the money to do any of these things. We looked into a different direction. What would be the most efficient way to look into the controller parameters and find the most optimized ones and repeatable ones. So that's why we investigate the Bayesian optimization. And what you see here on the top is the system basically looks at these the whole parameter space, which exists on multiple dimensions, and it interestingly looks at the full space. It's a global optimization system. It represents the function that is not known. This Gaussian is not known, but it represents it with Gaussian, so it really includes some unknown. It includes some redundancy. And it, by looking into these different parts of the whole dimension space, it finds the optimized parameters in a really short time. So what we were able to show is with applying these Gaussian processes and Bayesian optimization with different robots that have actually different magnetic properties, even though it was claimed that they were produced the same way, we saw that in the small scale it generated different locomotion modes. We were able to generate find the optimal control parameters that are repeatable and trustable. And here you can see at first, for example, this was the blunt approach of using two, for example, parameters for the controller. This was the belief that we started, but after the optimization, we saw that actually the whole space is more complex. So it also helped us to really investigate the full parameter space. So I'm going to skip some of the details here, but I hope that the premise is quite easy to understand. After a while, we wanted to upgrade our system. We put some fancy lights and a better controller, a better tracking method. And this is very similar in terms of what I have done with the squeezing method. We wanted everything to be optimized, automated so that we can go ahead and drink our coffee. We also implemented the automatic resetting mechanism and automatic locomotion detection mechanism, but basically looking at the steps of the robot, we were able to see if it's really walking or not. That was the thing that we were trying to optimize. We were trying to basically optimize the stride length of this little robot. So this allowed us to really investigate more in terms of changing the parameters and investigating different environmental parameters. For example, as I said that we were interested in putting these inside the human body, mostly in the GI tract, inside the stomach, which is a crazy environment for a soft robot like this. It is sticky, it is rough, it is viscous, And once, imagine that you don't have the repeatable control system, plus you're introducing this crazy world, and robot will deteriorate because the material is gonna go through some really deterioration while interacting with the environment. So what we wanted to do is not only we understand the parameters, but we also wanted to adapt these parameters along with the robot being deteriorated, along with the changes in the environment. So with this automation applied and with this fully reversible and repeatable system, we were able to investigate environmental parameters such as the adhesion, the roughness, and the viscosity of the whole medium. It was a big space. Of course, we used the same approach of Bayesian optimization, and we were able to go into the details. We did hundreds of experiments to see what's the limit for each of the robots, and then the Bayesian optimization were able to tell us what are the optimized regions for each of the robots and each of the environmental factors so that they can really keep on walking. For example, I will show you 3 videos here. You can see that you have one robot that is optimized in, for example, walking in a certain floor, but then you introduce the same robot to walk in an adhesive surface, you can see that it gets stuck, right? And we really don't want that. And the Bayesian optimization were able to really look into the different parts of the parameter space, and then it was able to find the optimal controller parameters such that the robot is now able to walk. The same thing applied to a rough surface. It didn't really work. When I say rough, basically it has a lot of gaps in it, cracks in it, so that the robot is small enough to actually fall into those gaps. You can imagine the same thing applied, and then the robot was able to walk. And the last thing we did was to show if it applies to walking in a very viscous fluid, because if you apply the same thing, you can see that the robot starts to basically swim. And the same optimization method was able to find the optimized method such that the robot doesn't really leave the surface, but still able to implement the walking. So this was, in a way, again, introducing machine learning control and modeling to continuous surfaces, continuous robots with a lot of feedback. But this was quite of like a cheating, because we were still using visual feedback for systems that were intended to be inside the human body, which is not really realistic, right? So that's why, as the next step, we investigated a different feedback system that is decoupled from the magnetic actuation. One of the efforts is to really use the same actuation methods, such as MRI, to both actuate and do the imaging at the same time. But I believe that is generating more problems than solutions. So one of the most practical things, after speaking with the doctors and practitioners, the best way to do this in the real world was to decouple the actuation mechanism, which is magnetic field, and the imaging method, which is in this case was electrical impedance tomography. We used a simple application method and electrical impedance tomography, which you have the robot, and through the electrodes, where you do a combination between, by reading the impedance between the electrodes, you see here in the round, like a circular formation, you're able to generate a map of the impedance. And by reconstructing the whole thing, the whole data that we read from the electrodes, you're able to generate some sort of a real-time position feedback. You can see it's still at the beginning, of course. It also has its own limits, because it has to be wrapped around, and it has to be inside a conductive fluid. But this was our intention, to really decouple and then go towards a full real-time feedback system. One can think of, for example, I always forget the name of this method, ultrasound, to use as an alternative method for imaging. So this was our method of introducing feedback systems. This was one direction, and the last direction I'm going to talk about was applying the Bayesian optimization to a completely different system. At that time, we were working with the materials department, the advanced magnetic materials department at Max Planck Institute, Modern Magnetic Systems, I'm sorry. And they were producing thin films in the nanoscale, and they were applying to Bosch, the sensors of the electronic sensors of Bosch. At that time, they were interested in covering the surface of these circuits with thin films. But their problem was that if the thin film is not properly produced, it has gaps and it generates corrosion in the long term. So they didn't want that. And you can imagine this is a nanoscale fabrication method, which is also a crazy, huge dimension sort of fabrication method. They wanted to see if we were able to apply the same Bayesian optimization, which is able to find the global optimum in very limited number of steps. We applied it, surprised the collaborators, and we were able to find the optimized fabrication methods, and the etched area, which is basically the error, the holes in on the film, was reduced basically almost half of it in less than 10 experimental steps. So this does not only save money, but also save time, and then it also at the same time gives you an idea about the optimal parameter step. So those were basically the last things that I have done. I think I have spoken so much. I'm sorry about that. Maybe I can talk how I am now applying these things in the institute. I'm just going to give an overview, maybe just 5 more minutes, then I'll be done, I promise. So basically, I am bringing now form, function, and learning into the systems here. We are now working with robotic systems that are, again, they're more in the mesoscale in the applications. There's, again, work, health, environment, and mobility. But I am able to bring these expertise and application to the system as well, in terms of form, about using rigid systems, using soft materials, how we can model and control them, self-assembling systems in terms of using maybe swarm and bringing an external control to swarm systems, or self-assembling systems maybe in the multiple robot configurations, and of course machine learning to extract the models of unknown systems, such as in soft continuum systems and statistical robotics. So there are a lot of labs that I'm also leading here, not hands-on with each of them, but there are a lot of connection points between what I do and how it can be how my research is actually connected to them. You can see there are different fields here, and all of them have fundamental connections. Maybe one last thing I can say, those are the projects I'm currently now I'm involved in. I am a part of the research team. I have also written some of these proposals myself with the team. So these are all large-scale projects. For example, KI-Fabrik is one of our lighthouse projects, which is aiming to build an automated robotic factory in Munich, in central Munich, so that we generate knowledge for industry and we produce actual products. We now are working with BMW and Wittgenstein, for example, to produce their own products. In the factory, that is actually also self-assembling. So we have mobile systems, mobile robots that can reassemble within, so that they can produce everything that is necessary. So I'm a PI in this. I'm also the one of the architects of the factory here. And we are building in the Deutsches Museum. I don't know if you know it, but it's one of the largest science museums in Europe. So the whole basement of the museum will be a factory now, and we are still building it. Another one is 6G Life project that we are collaborating with University of Dresden and Technical University of Munich. It's quite a large one. The first one is, I think, about 20 million euros. The second one is something around 70 million. Germany realized that it's really slow in terms of communication technologies, and they really wanted to push, so that they are now the leads in the 6G Life. I'm not a communication guy myself. I'm more interested in robotics. What we do here with my team is to build a surgical robotic system with tactile end effectors, with visual tactile sensing, such that it could operate with high loads of data with 6G. So this is our intention of using 6G to bring robotics to a different level. So we are now working on building this robotic system and teleoperation, such that the robots are in one location and doctors in another location. This is what we are trying to do. One other project is One Munich with LMU, which is another big university in Munich, and Helmholtz Institute. We are trying to work on bringing human embodiment and system agency in explainable AI. Again, this is an effort to bring robotics into human world, so that everything is explainable, not only the hardware and software, but also the AI and decision-making systems. And in that, I am working on building exoskeletons, prosthetic devices, and lab assistants. And the last thing I'm going to just briefly talk about is something we have recently got from Horizon program. It's this new European network of excellence. In this one, we are interested in bringing different European robotic institutes all around Europe. I think we have 25 of them at the moment as partners. The idea is to use robots and explainable AI and energy aware systems to address the circular economy, so to address the Green Deal problem. So now we are working on building robotic systems that can work with minimum energy, and they can interact with humans and extract that information such that this information can be used by industry to reduce the energy cost of their production. So I guess with this, I am going to finalize my talk. So thank you very much. This is not a one-man job. This is a combined effort of everyone. I would like to thank everyone who has contributed. Some of the names are already here from different universities, different institutes. We don't have a group picture taken from MIRMI yet, my institute, because it's a huge group. But I would also like to finally thank the whole taxpayer community, because without their tax money, none of this will be available. So with this, thank you very much for your attention. And I would like to now take your questions. And I apologize if I have taken so long.